Well, we could keep talking about counting for a long time. There's lots of things to think about, but it may be a good time to draw to a close our discussion on counting. After all, if we do want to move on and talk and think about addition, subtraction, multiplication, division, fractions, algebra, geometry, trigonometry, calculus, and everything beyond and in between and in and around all those ideas, then we do need to move on from counting at some point. But what we've begun to do here really, the thinking styles and some of the approaches to dealing with mathematical reasoning, what we've begun to do here is going to help us carry us all the way through algebra and geometry and calculus if we keep on with this spirit of discovery and research. So let's try to collect some of the lessons, what I would see to be some of the important lessons from this experiment in researching counting. There's so many things that just counting alone gives us to think and do research about. Lots of things could be said. Just look at some highlights here. One thing that we did over and over again in these exercises was to do things in as many different ways as we could possibly think of. For example, at the very end here, we wrote out the number of marbles that we had on that cover page in 4 different counting systems, and we even thought about other counting systems beyond these. But this is a good start. We thought about how could I express the same number of marbles in a number of different ways. We considered an approach to solving mathematical difficulties or problems, which is always to consider special or small cases and see if we can then generalize that into bigger ones. Way back when we were just trying to start thinking about how we might keep track of our marbles if we didn't have the numbers that we're used to knowing, we considered, well, if we have a really small number of marbles, then we could just match them up with our fingers and remember how many fingers we use. That was a special case, and before long we ran out of fingers and we needed to go further from there. But even as we moved on and we realized that putting these marbles together into these square or rectangular patterns, and then we ended up turning those patterns into packages of packages. But that was, again, all came back to the idea of finger counting, where we were going to match up the sizes of the package with the fingers on one hand. And so the earlier ideas actually did carry over into some of the later ideas and moved us forward. We also talked about how there's a difference between the notation and the just cultural or conventional mathematical language that we can invent to describe concepts to each other, like the notation, the numerals that we have, the Arabic numerals that we have for expressing 1, 2, 3, 4, 5, 6, 7, or the fact that we use a two-handed system to begin with, 0 for nothing. All of these notational choices are just culturally based, and for the sake of a common mathematical language, it could be different. But then there's also discovered patterns such that if we have this common notation that we can agree with, if we all agree on a common notation, then someone from China or from the Middle East or from Europe or Latin America or North America, we can all discover the same universal patterns. If we're using the same notation, the same patterns will emerge and express themselves in the same universal way. So math has this nice universal property that in some sense it's the same for everyone. Now the caveat being there, if we've agreed on the same, we're all going to use the same notation, then the properties that we derive are universal for everyone. But in either case, kind of a follow-up on this, point 4 is kind of a corollary or follow-up on point 3. There's nowhere that we just simply have to say, oh, that's just how it is. In some cases, we say, well, that's the way that our mathematical language just was agreed upon by our ancestors at some point, or maybe just a few generations of mathematicians in our past. We agreed on certain notation. So sometimes that's the reason we do things, is just for the sake of having a common communication. Sometimes things are there because there's an underlying pattern, and we need to realize it may not be obvious. If we just learn the method for doing mathematics, we may not realize the underlying pattern on how things fit together and are done for a very good reason. Why do we have, when in the normal math system that we use, where we have a ones position and a tens position and a hundreds and a thousands and a 10,000s? Well, the fact that we're using a two-handed system, that's just culturally based. But the fact that these different columns are a good system for counting, well, that's based on this packaging structure that we found to be a universal pattern that works as a very conducive way for describing structures of ordered marbles or any kind of subject. So in any case, there's different reasons behind the reasons that we do things in the mathematics, but there's no time when it ever just comes down to, oh, that's just the way it is. No, things are there for a reason. It's always good to ask why, and to research. And if the person that you ask, the parent or the teacher or the supervisor, someone that you ask, if they don't know why, well, you can keep investigating, keep thinking about it, keep doing research, and try and figure out. There's always a reason for why we do things in math. A little bit more specifically, those are kind of some general principles. A little bit more specifically, we found that this system of packaging with packages within packages within packages within packages was a very good way to keep track of both large numbers of objects. So we could get really large. Remember this pattern, and this could continue. I mean, this is a few layers thick, but we could keep going and going and going. This is 1, 2, 3, 4, 5 layers thick. But we could keep going, and the number of marbles is just going to increase rapidly. In fact, it's exponential growth, to be precise, if you know that term. But in any case, this packaging system works very well for describing large numbers of objects. But when we start talking about leftovers, it also works quite well for describing small numbers or any numbers of objects, just depending on how big of the packages have to be. And so this system was not just turned out to be a good way to think about things, it's also very practical. It's the two most common systems of counting things or doing math in the world. The two most common notational systems or ways of expressing things are the computer language and the two-handed human system, base 2 and base 10. So this system of packages is actually used both by computers and by humans, although with different package sizes, because of we've got fingers on our hands and computers have open and closed circuits. And then finally, another little interesting note, but it just seems to affect a lot of mathematics, is this special case of the number 0 that has this really special case, and we just realized that you might think of, well, 0 means nothing, and so nothing is insignificant, right? Well, nothing can be extremely significant. When we're talking in computer language, all you have is ones and zeros. If you took away the zeros, all you'd have is ones, and what could you do? Then you're just left at, if all you have is ones, then you may as well just, if I have just ones to describe my marbles, and I have to draw a 1 for every marble, then I may as well just be drawing all my marbles to begin with. But the zeros have a significant role in telling us how our packaging system works. So I've got none of these packages, none of these, none of these, and this 0 turns out to be quite significant. And if we didn't have it, there would be so much confusion. We wouldn't know, how. Well, we'd either have to start, drawing our. We'd either have to change our notation to start drawing our package sizes. This is going to be something like this, and this is going to have a lot of packages around it. Or we'd have to do some other notation, but the 0 gives us this placeholder to divide up the slots of ever-increasing larger package sizes. And 0 just has so many significant roles in mathematics. We use it in algebra. It helps us to solve algebraic equations, and it also sometimes trips us up to give us wrong answers if we use it wrong when we're doing algebra. And 0 is significant in calculus when we're taking limits and everything is going to 0, but you need to compare how fast something is going to 0, something else is going to 0, and it just comes up all of the time, and it messes up a lot of our equations when we divide by 0. So 0 is this very significant number, a very significant concept for describing nothing. It's a bit strange, but the concept of nothing is actually very significant for describing some things. Now, I've got one more assignment for you before we close off this section on counting, and that will be the next video, your final assignment before we move on to something else beyond counting.